Before we are going to climb further up in the cosmic distance ladder, we need to talk in this episode about a couple of basic principles that are underlying the methods that we are going to discuss later in this seminar. These deal primarily with the relationship between brightness and distance. From the brightness as we see it, we cannot determine the distance to a star, because a very massive star at a great distance can look fainter than a less massive star that is nearby. So we need to know more about that star. And this extra information is very generally what we call the luminosity of a star. That is an intrinsic property of any star. Now, what is luminosity? You may not have heard that word, but you know how many watts is a light bulb. The physical quantity that we express in watts is called power. But the unit of watt is actually energy per unit of time, energy per second. And the unit for energy is joule, so a watt is a joule per second. We use this in everyday situations, like, for instance, light bulbs. What we call luminosity for stars is exactly the same thing. It's just a different name. But the unit also needs to change, because if we look, we can calculate this from observations, that the luminosity of our sun is 3.83 times 10 to the 26th watt. So if we express luminosity of stars, and our sun is only an average star, in watts, you get extremely large numbers. So what we do in astronomy is we use another unit for luminosity, for the power of a star. We choose our own star, the sun. Its luminosity has a luminosity of 1. So that is the unit of the luminosity scale. Our sun has a luminosity of 1 by definition. Now let's go back to the brightness and distance. And this is a very simple thought experiment. You can actually do this yourself with a couple of friends as well. You have two torches, and one torch is more bright. It has a larger number of watts in its light bulb than the other one. The one at the left here in the top image is the brighter one. There they are at some distance from you as you observe it, and they are at the same distance. Well, the more powerful one is visually more bright than the other one. But now you ask your friend who's holding the bright torch to go further away. What you see here in the bottom image is that the torch which has the most luminosity, if it was a star, is, because it's further away, is looking dimmer, is less bright as you see it than the other torch, which is still at the same original distance. So this demonstrates that if you do not know the wattage of the light bulb, so to speak, then we cannot know the distance from brightness. But if we do know the wattage of the light bulb, and in the case of stars, if we would know the luminosity of the star, then we can figure out the distance. So then you have a relationship between distance on the one hand and the brightness as we see it, as well as the luminosity of the star on the other hand. This relates to the inverse square law. I've talked about this in the seminar Falling in Space. If you look up the episode about Newton, principle of inverse square law actually originates from Robert Hooke and Isaac Newton. They were actually in a dispute between themselves, who was the one who came up with this idea. But the principle of inverse square law, as we discussed there in that episode, was very important for Newton when he was putting together his universal law of gravity. But this is a very general principle in physics. It holds for many different phenomena, like sound waves or electric fields or light, as in this case. In the general word for brightness would be flux in this concept, this physics concept. That is the brightness that we see at a certain distance. But if you start with a source that has a luminosity, which is called L here, this radiation is spreading out in all directions equally. You take a unit of surface area at a certain standard distance, and then you calculate the flux, which is the radiation that is originating from the center as it has been spreading out over that unit of area, which for a sphere is 4 pi r squared, where r is the radius of the distance. So this flux, as we call it, is the radiation that is spread out over the surface area here, this unit of surface area. But if you go twice as far away, then you will see that the luminosity, the radiation, is spreading out over a surface area which is 2 times 2, which is 2 squared times as large, 4 times as large. The distance increases 3 times. The area over which the radiation is spread out is 3 times 3, which is 3 squared, or 9 times. And the flux that you observe at these various distances diminishes, of course, with the distance. This is why this in the denominator, the r here is the distance. So this is why it's called an inverse square law. It's the square of the distance, and it's inverse because with greater distance, the total flux diminishes, decreases. So that is the principle of what we call the inverse square law in physics. This is a general form of this formula. F is the flux, but that's in where we are going, that will be the brightness as we see it. L, capital L here at the top, that is the luminosity of the star. We need to know that if we want to calculate the distance. But if we know it, you plug that in here, and then r is the distance to the star. So you can calculate r if you know both the luminosity and the brightness as we see it, as we observe it. That is the principle, the inverse square law principle that we use in many applications of distance measurement in astronomy. For the other principle that we need to discuss, I need to refer to the magnitude scale. It was Hipparchus, which I mentioned also in the first episode, who classified brightness of stars, and he came up with the term magnitude, and he proposed a certain scale of magnitude from bright to less bright. It was all based on visual observations. He didn't have photometers like we have today, that you can accurately measure brightness. But he came up with this scale to express brightness as we see it. And it is still very much used in astronomy, but it has been refined in the 19th century, that scale. It has now been mathematically, carefully, accurately been defined. The first magnitude is 100 times brighter than the 6th magnitude. That means over 5 intervals of magnitude on the magnitude scale, you will have a factor of brightness from 1 to 100. Anywhere on the magnitude scale, you have over 5 interval distance, you have that factor of 100. Mathematically, that means that each interval is 100 to the power 1 over 5. You can calculate it on your scientific calculator, that's 2.512. In other words, if you multiply 2.512 5 times with itself, so you take the power 5 of 2.512, then you get 100. You can verify this yourself. And this is then a logarithmic scale. So we need to use logarithms. If you're not familiar with that, I have a link in the ebook, and I will explain this in the simplest way I can. And on that magnitude scale, the brightness that we see is called apparent magnitude. The symbol is lowercase m. Here you see an example of magnitude scales for different objects. The 0 point is has been chosen, the star Vega, northern hemisphere star. The current latest value is not exactly 0, but this is in principle the 0 point of the magnitude scale, and anything that's fainter has an increasing number of magnitude. But because we can also observe much brighter objects, this scale also allows negative values. And more bright means a negative magnitude, more bright than the star Vega. The second brightest star in the southern hemisphere is Canopus. It has a magnitude of negative 0.7. Sirius is the negative 1.5, etc. All the way up to the sun, which of course is extremely bright, has a magnitude of negative 26.73. So in summary, the magnitude scale, we use that to express brightness as we see it, and that's called apparent magnitude. Symbol is lowercase m. It indicates the brightness as we see it. And the scale runs opposite to the actual brightness. So a brighter object has a smaller magnitude, all the way into the negative range. And it's centered around Vega. And again, the mathematical definition is that 5 units of magnitude corresponds to a factor of 100 in brightness. And this is where this number 2.512 comes in, and I'll use that in a minute. So now we can talk about a concept which is called a distance modulus. If you go back to luminosity, which we need to use once we know it, we need to use it in a formula to calculate distance. We can actually express luminosity also in the magnitude scale. And then if we do that, we call it absolute magnitude, capital M. It's a bit confusing. You really need to know what you're talking about. And if I talk about it, I sometimes make a mistake. Absolute magnitude is the luminosity, capital M. Apparent magnitude is the brightness as we see it. Now, the difference between those two magnitudes, apparent magnitude, lowercase m, and absolute magnitude, actually luminosity, that is a measure for the distance. And this is why it's called a distance modulus. It's kind of a mathematical term. I will explain this, but it involves, as I said, a little bit of logarithm. If you have two stars, star 1 and star 2, then the ratio of the flux, or the brightness as we see it, of any two stars relates to their magnitude in this form. This is a consequence of the fact that this is a logarithmic scale. Remember, we had 100 to the power 1 over 5 for one interval. So that is the scale of the magnitude unit from one magnitude to the next. But now we have a ratio of flux of two stars that have a magnitude, apparent magnitude m1 and apparent magnitude m2. And the difference between those two over 5 as the power of 100, that is then the ratio of those two fluxes, those two stars. But if we now apply this to one star, where 1 is the absolute magnitude, capital M, that's the luminosity, which is actually defined as the apparent magnitude at the distance of 10 parsec. It is, if the star would be at the standard distance of 10 parsec, then the apparent magnitude, that would be the absolute magnitude of that star. That is the luminosity expressed in the magnitude scale. So if we now use this relationship here for one star, but then the one component is the absolute magnitude and the other one is the flux that we see, this is the apparent magnitude, we get this ratio. So the flux of the star at the standard distance has the absolute magnitude here, the capital M, and the flux of the same star, but at the distance that it has, which we want to know, is the lowercase m, the apparent magnitude. So this formula now expresses the ratio of the luminosity of the star expressed in the magnitude scale with the brightness as we actually see it at the actual distance that it has. And this here is what we call the distance modulus, 100 to the power of lowercase m minus capital M. So that's the consequence of looking at the definition of the magnitude scale, which is a logarithmic scale. So here I have the original inverse square law relationship for the flux at the standard distance, which is the absolute magnitude, and for the flux at the actual distance that the star has. Here we have the distance in 10 parsec, which is the definition. Here we have the unknown distance in parsec as capital D. So those are the two relationships basically derived from the inverse square law. If we now insert those two expressions in the original relationship that I have on the previous slide, the F10 over Fd is this. We insert this expression for F10 and this expression for Fd. What you will see is that both the L and the 4 pi cancel out. So it becomes a really simple formula. It becomes d over 10 to the power 2 squared equals this right-hand side, which is the same. The square is because you had here the distance squared. So this is then a relationship which expresses the distance to this difference, which we call the distance modulus. And now we can do the inverse of logarithms. You can take the logarithm of both sides to make the distance modulus, m minus m, explicit. So this is the formula, the final form that we want, where this is the brightness in the magnitude scale that we see. This is the luminosity and the magnitude scale, and d is the distance. And 5 and 10 are just factors, and this is the 10-based logarithm. So here you have the formula for the distance modulus expressed in the distance that you want to know. So that's the mathematics which we need to apply this principle of using a distance modulus. It sounds very theoretical what I'm explaining up to now, but in the next episode, I will start with a technique that uses this distance modulus to find distance. Here's an example to try to explain it a little bit more in detail. Suppose that we have a star which has an absolute magnitude of -1, which is the magnitude at the standard distance of 10 parsec, and an apparent magnitude, as we see it, as of +14. So it's a fairly faint star. What is the distance to that star? We should be able to calculate that from this formula. Okay. 14 is the lowercase m. 1.0 is the capital M. So it's 14 minus 1.0, which is 14 plus 1, which is 15, is this side here, 5 of the 10-base logarithm of d over 10. And then we take the factor of 5 here to the other side. So we divide by 5, you get 3 equals the 10-base log of d over 10. And now we can get rid of the logarithm by taking the power of 10 on both sides. So we take 10 to the power 3, which is here, equals d over 10, because the logarithm then disappears. This is a trick when you use logarithms. The base number is 10, so if you take this expression to the power 10, then you get rid of the logarithm. So we end up with this, and now we move the factor of 10 in the bottom to the left-hand side, so it becomes 10 times 10 to the power 3 is 10 to the times 4 equals d. So now we have the distance here is 10 to the power 4, which is 10,000. And we know that the unit of distance is parsec. So the distance to this star, based on these two values here, is 10,000 parsec. This is how it works. So I have discussed two basic principles now that we need to get further into the discussing techniques to measure distance. The first one was the inverse square law, which is a very general application that we will use several times in most of the other distance measuring techniques that we are going to discuss, where F is the brightness that we see, L is the luminosity, and R is the distance that you want to know. So this is the relationship of the inverse square law. If we want to use this magnitude scale for luminosity, which is the capital M, we have this formula for the so-called distance modulus. So I'll show you in the next episode how we are calculating distance from these relationships.